Hello and what's up to you all wonderful and awesome mindsetters. It is a lovely Tuesday and it is time for Physical Sciences, a time to learn more and learn extra. I hope you had a great day at school, but otherwise you'll share all of that with me on Facebook. My name is Abram and I'm here to be your guide and to be your help, of course, with Tracy. How are you, Tracy?
I'm well, thanks, Abram. Good to see you, mindsetters. And mindsetters, I really hope that you've got your thinking caps on, because today we're going to be doing lots in terms of chemical change and representing chemical change.
Awesome. Let's not waste any further more time. Let me tell you, mindsetters, all you need to do to join us in this lesson, it is simple. Get onto facebook.com/learnextra. Like the page, share the page with everybody, your friends, your classmates, even your teachers. Tell them to be on the page, because that's where you can also ask some of your questions if you're struggling. But also, we have the notes links that are posted on Facebook, both viewing and downloading links. So you have the direct access to those links on facebook.com/learnextra. Connect with us on Twitter also by just following us at LearnExtra. And remember, you're standing a chance of winning this awesome Casio calculator, proudly sponsored by Casio, by simply doing the test yourself questions. On the notes, you have those questions, but we have the link on Facebook where you can send us your answers. So stand a chance of winning this awesome calculator. We'll announce the winner of last week's show later on the show, Tracy.
Perfect. Thanks so much, Abram. So, mindsetters, I said to you today we're going to be doing representing chemical change. And this is foundational. If you can get this right today, you will be set up perfectly for grade 10 and grade 11 and grade 12 physical science, because we're wanting to represent chemical change. And we discussed in our show a while back about physical change and chemical change and the differences between those. But it's very important to be able to then represent chemical reactions and write formulae. So, and that's going to stand you in good stead all the way through your chemistry career. So, representing chemical change. And in this lesson, we're going to focus on using symbols to represent chemical reactions. We'll practice writing chemical formulae, and that's something that I know students do struggle with, so we need to make sure we get that right. And then I think, Master K, you asked a question a while back in our previous show about what is a simple way to balance equations. So I want to tackle that with you today as well, and we'll be looking at balancing those chemical equations. Because, of course, the reality is that equations don't happen without being balanced. They have to be balanced. Sometimes we write them if they're not balanced because we're writing them in a simple format, but they actually all have to be balanced, and they can't occur without being balanced. So, because matter cannot be created or destroyed. So, I want to start with a challenge question, because, and I've given this to you as a word equation. So I've given it as a description, and what you need to do is go and write the individual formulae and then balance it. So, your challenge question: write a balanced symbol equation from the following word equations. So from the description, go and write it. Aluminium reacts with solid copper 2 oxide to produce copper metal and aluminium oxide. I'll leave that with you. So, turning now to the summary. As we think about it, I want to remind you, when we spoke about a physical change and when we spoke about a chemical change is quite significant, because a chemical change, new products are formed. When a chemical change takes place, new substances are formed in a chemical reaction. So old bonds break, new bonds form, and a new substance with different properties will be formed. New substances even. So we're thinking chemical reactions. Whereas physical change, remember we said physical change, particles could be moving further apart. They could be going through a phase change, but they're still the same substance. Now we need to write formula, because we're dealing with chemical change, substances breaking old bonds, forming new bonds, new substances forming. And so it's very helpful to be able to represent that and to describe the chemical change. So that could be described in words. It could be written in symbols. And then it needs to be written as a balanced symbol equation. And the reason we say this is because across the world, scientists need to be able to communicate. And with the value of the internet, we can communicate with people in all different countries. And so if maybe you were studying something about magnesium oxide, you want to maybe be discussing with another person, another scientist across the world, you also need to be able to represent that in a written format. So very important that we can identify and write symbol equations and then balanced equations. So a few key points. Well, to start off with reactants. Reactants are the things on the left-hand side of the equation, and the products are what is formed. So they will be on the right-hand side of the equation. An arrow is used to represent the direction of the reaction. Now it's important to note, so reactants are going to be changed into products. It's important to note actually that some reactions are reversible. So the arrow could go the opposite way, or both ways I should say. And we'll do that later on as we get to reversible reactions. But important to identify here that an arrow pointing in one direction is showing reactants turning into products. So I mentioned magnesium oxide. Let's think through this equation as we discuss writing formulae and balancing equations. Magnesium burns in oxygen to produce a white substance, magnesium oxide. In words, notice we've got there the words magnesium plus oxygen is forming magnesium oxide. And notice the arrow. So on the left-hand side here, we've got reactants. And this is our product. In symbol form, well, I now want to write each individual substance. So magnesium, Mg, plus oxygen, O2, forms magnesium oxide, MgO. It's incredibly important to identify the original, the true formula for each substance. So what you should note here is magnesium metal as an element just by itself. Oxygen, O2. Hold on a moment. Look at this 2 on the bottom here. Notice that it is a diatomic substance. So each substance must be written in the correct formula. Remember, some elements exist as diatomic molecules, and oxygen is one of them, O2. I've written out a list here: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All the halogens are all diatomic. When we say something is diatomic, it means 2 atoms combined together. Di meaning 2, atomic, atoms. So, but something's only diatomic if it is by itself. The reason we say that is because it's so reactive, it can't just be one individual atom. It will pair up with its next neighbor. So, oxygen, O2. And so when we write this formula, magnesium oxide, magnesium plus oxygen, the oxygen must be written in its diatomic form. And that forms magnesium oxide. Now I've made a note here that this is not yet balanced, because we're going to come to balancing. But I want you to identify we've gone from words to a symbol equation, writing the correct symbol for each of those substances. So this is where many times students come unstuck. And that is writing the original formulae, writing the correct formulae for any substance. So I want to talk through covalent bonding and how to identify covalent substance, how to write formulae for those, and then I want to talk about ionic. There are almost 2 methods, but obviously it does depend on what you're dealing with. So if we are dealing with covalent compounds, we would consider the group number. Now when I say the group number helps us find the valency of each substance in the compound. So I'm going to my periodic table. Group 1 would have a valency of 1. Group 2 would have a valency of 2. Group 3, I'm going to jump across to group 13, would have a valency of 3. Group 4 would have a valency of 4. Group 5, well, now it's getting closer to the end, group 18. So how many bonds does it need to make? Only another 3. Okay, so Group 15 should have a valency of 3, group 16 a valency of 2, group 17 a valency of 1, group 18 a valency of 0. And if you can work with the valency from the periodic table, that's going to significantly help you. And we spoke a lot about valency way back when we were doing chemical bonding, so you might want to go and recap those. If we go back to our notes, the valency represents the number of bonds the substance can make. For each substance, draw out the bonds as little arms and link each. So I've given an example here of ammonia. I'm just giving myself some space. Ammonia is made up of nitrogen and hydrogen. So I'm going to start by drawing the nitrogen down here. Nitrogen. It has got, let's draw a Lewis diagram, 1, 2, 3, 4, 5 valence electrons. I get that because going across, we find nitrogen. There it is. It's in group 15. So it's going to have 5 valence electrons. Coming back here, notice those 5 valence electrons. How many bonds can it make? Look, it's got space for a bond in there, a bond over here, and a bond over there. Okay, so it's got space to make 3 more bonds. And it wants to make 3 bonds. Now I'm going to take those arrows away because what I would like to show is hydrogen linking up with this. And hydrogen can make, is in group 1, there it is. It's a non-metal, so watch out for that. It's a non-metal, but hydrogen will be able to fit and make a bond here. Hydrogen can make a bond there, and with this one as well. So in a sense, you've got 3 single covalent bonds. Covalent meaning sharing bonds. Group 15 can make 3 bonds. Group 1 can make 1 bond. The formula, as you can see, I've drawn from the Lewis diagram. I could represent nitrogen with its 3 bonds. I'm going to show this lone pair at the top because that will help you. And hydrogen, hydrogen, hydrogen fit in there. Very easily I can identify the formula is NH3. Okay. The lone pair at the top, a lone pair is already paired up with 2 atoms, so 2 electrons within the atom from the same atom. So it's already paired. It's not unpaired. So the formula here, NH3. How did I get that? I looked at the valency, how many bonds each substance can make, and I linked up the little arms. Hydrogen can make 1, nitrogen needs to make 3. And so the formula, NH3. When we go across, so we've discussed covalent bonding. Covalent happens specifically when you're dealing with a non-metal and another non-metal. That's how you can identify covalent bonding. If we're dealing with ionic bonding, so ionic substances that have formed ions, substances that have given electrons away or taken electrons up, they have formed charged particles or ions. And so we want to look at the charge to help us write the correct formula for each substance. So ionic compounds, the valency, remember we're back to that keyword valency, how many bonds it can make. Specifically here for ionic substances will represent the charge on the ion. So it's either going to be a positive charge or a negative charge. Quite easy to identify. Things that have few electrons, metals, only got group 1, got 1 valence electron, group 2, 2 valence electrons, group 3, 3 valence electrons. They've got so many more to gain, they would rather, easier, just to lose. In terms of energy, to give away electrons, much, much easier. So, metals will always have a positive charge, and I'm going to write a little plus sign next to the metals. Will always have a positive charge as they give away their valence electrons. In comparison, non-metals will gain electrons. So if they're taking up extra negative particles, negative electrons, they're taking up extra electrons, they then overall would become negative. So when they gain electrons, they would form negative ions. So next to nonmetals here, I'm writing a big negative. This is always done in order to obtain a filled outer energy level, and that is always the purpose. Remember, that's the purpose of bonding, for substances to become more stable so that they have a filled outer energy level. In doing that, we can say, okay, well, then if I'm dealing with something in group 1, it would form a 1 plus charge because it gave away its 1 electron. If I'm dealing with something within group 2, I will form a 2 plus charge on that substance because it must have given away 2 electrons. And so you can work your way through the periodic table. So I've given a quick little summary here. Group 1, and maybe I shouldn't have used hydrogen. Let's change that to something like lithium, would form a 1 plus charge. Remember, hydrogen is a non-metal, so very often it would involve not the complete transfer of electrons. It usually would very often undergo covalent bonding, depending on what it's bonding with. But so there we've got lithium is in group 1, a 1 plus charge. Magnesium in group 2, a 2 plus charge. Aluminium is in group 3. It's going to have formed a 3 plus charge. And the way you would work this out, if I give myself some space at the bottom here, you could literally write up aluminium has got its 3 valence electrons. When it bonds, what's going to happen very often is that it would give those electrons away, and so is going to be left aluminium overall with a 3 plus charge. And that's what we mean. But what I don't want you to have to draw this out every time, because I want you to be able to look at the periodic table and say, I know what's going to happen. It's going to form aluminium 3 plus. Okay? So, heading back to our little table here. I'm leaving out group 4 and 5, or 14 and maybe we should call this group 13. Then I'm leaving out 14 and 15 because, again, they're non-metals, so they would form covalent bonding very often. Group 16 would gain electrons because it's only got 2 more to gain, so it's going to gain electrons. Group 17 would gain 1 to get to the filled outer energy level, and group 18, 0. The key issue here is that we want to know the original charges so we can balance the charges. And I have got a couple of examples here to show you what we mean in terms of balancing the charges. We dealt with magnesium oxide earlier in today's show, but I thought it would be helpful to point it out to you again. Magnesium, Mg, 2 plus. How do I know that? It's in group 2 on the periodic table. Oxygen would form 2 minus. Why? Well, because it's in group 16 on the periodic table. And the issue then is simply to balance the charges. So I'll focus, balance the charges. So notice I've got a 2 plus and a 2 minus. It is already balanced. MgO is my answer. Let's do another one. Beryllium chloride. Beryllium I've already written there as a 2 plus. Chloride a 1 minus. So let's write the formula. It would be Be. I've got 2 positives. I'm going to have 2 of the chlorides to give enough negatives to even out those charges. We want to make the charges balanced. We want to make this thing overall neutral. Okay? Recognize ionic bonding. We want the overall charges to be balanced. Lithium oxide. So I've got the original substances there, lithium Li plus, oxygen O2 minus. We're writing the formula. So we're balancing the charges. Lithium, I've got only 1 positive, so I need to have 2 of them with the 1 oxygen. Calcium chloride. Calcium Ca2 plus, because it's in group 2. Fluoride F minus because it's in group 17. And once again, I'm going to have two negatives. So, sorry, Ca, F, 2. Now I want to stop here for a moment and focus on this F2 story. That is not in any way saying that fluorine has to have a 2 there because it's diatomic. No, 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 no. Something's only diatomic when it's by itself. This is the F2 there. It could be aluminium fluoride would be AlF3. It's not got anything to do with being diatomic or not. Rather, it's got to do with balancing that charge. Okay? What happens if you don't know from the periodic table what the charge should be? Well, then we're going to tell you what the charge should be, because something like iron has a number of what we call oxidation states. It's got a number of charges it can form. So I would have to inform you, tell you in the question what the charge is in this specific case. So iron 3 oxide, notice that Roman numeral behind the name of the element in a compound indicates the charge on that element. And so immediately I'm writing, oh, it's iron, so it's a metal, it's positive, and it's tells me it's 3, so Fe3 plus, O2 minus, because that's for oxygen. I can work that out. Now I need to write this as a balanced formula. So Fe, I must have 2 of them to get to plus 6, and oxygen I would have to have 3 of them to get to minus 6, so that my charges balance again. Okay? What many people do here is actually do a little cross multiply story. I don't want you to focus on that. I want you to focus on what will get me overall charges balanced. Here I have to have 2 of the ions and 3 of the oxygen ions to get the charges to balance. Lastly, when we speak about ions, I think it's helpful for you to go and learn and memorize a few polyatomic ions. Now, poly means many, atomic, atoms, and an ion is a charged particle. So, they are ions, polyatomic ions are ions, charged particles made up of many atoms. Okay, very helpful. They are useful to know. And I would recommend that you learn these 7, at least. Okay? So that when you come across an equation, you're not struggling and thinking, what is a carbonate again? It's 7 simple formulae. Go and learn them. Do a quick quiz with a friend and make sure that you've got them in your mind. They're going to stand you in very good stead. So ammonium is NH4 1+, hydroxide OH minus, nitrate NO3 minus, carbonate CO3 2 minus, sulfate SO4 2 minus, phosphate PO4 3, and I think my minus is gone there, 3 minus. I think we need to stop and take a short break now. I hope that's helped. When we come back, we're going to be dealing with balancing equations. So Abram, over to you.
I must say we really need that break. Yeah, that was quite a long one. Well, a warm welcome also to the mindsetters that are tuned in. Tell all your friends to also tune in, because we'll see you after this break. Welcome back, Mindsetters. Now looking on the page, facebook.com/LearnExtra. There's some Mindsetters that are enjoying the show, Tracy, such as Tato saying, enjoying the show already. It is a bang. Thank you so much, Mindsetters. And up here, welcome to you, Lawrence. Welcome to you, and Banyana. Welcome to you too. Tell all your other friends and also help one another on the page, because that's the spirit of Mindsetters. If you're struggling, we're here for you.
Awesome, absolutely, Mindsetters. We are here for you, and we want you to ask your questions, because this is fundamental stuff. And that's why I'm taking a bit more time going through it, because I really want you to catch this. And I know, Master K, you asked a question a while back about balancing equations. And so today, we're going to be tackling that in this segment. Now, when we speak about a balanced equation, what are we meaning? We mean that matter cannot be created or destroyed. So the number of atoms of each type that you started with, you must end up with. Okay, because that stuff can't have come from nowhere, and similarly, it can't just go into nothing. Okay, so what we're saying when we balance equations is that it's just a counting game, actually. The number of atoms of each element in the reactants, so at the start, must be the same as the number of atoms of each element in the product. In order to balance an equation, we have to put big numbers in the front. Now we call those big numbers coefficients. Maybe in maths, if you're doing like 2x plus 5, the big number 2, that is a coefficient. So we can take coefficients and place them in front of the reactants in the products until the number of atoms of each element is the same on both sides of the equation. Recall that I've spent a long time with you talking through writing individual formulae, and once you've got that formula, it's the correct formula for that substance. Taking it that you've done it correctly. Once you've got the correct formula, you can't go and change that formula. Okay? It is the correct true formula. So, what we're saying is that do not ever change any subscripts, as this would change the identity of the chemical substance. For example, we couldn't balance the reaction below, it should be, by simply putting an extra oxygen on water. And I want to write this equation out for you. Okay, so if I've got hydrogen plus oxygen forming water, H2O. You might say, all right, well, let's do a quick tally. Hydrogen atoms, oxygen atoms. On the left, notice I'm pretty much doing a little left-hand side versus right-hand side. Left-hand side, I've got 2. So 2 on that side, 2 on that side. Perfect. Oxygens, I've got 2 and only 1. Problem, it's not balanced. It looks like I've got 2 oxygen atoms and it's going to only 1 oxygen atom. So where did the other one go? Well, the reality is that's not possible. So instead, it must form 2 water molecules. And what we're saying here is that it is not true to go and put another 2 in there. That is completely wrong. Why is that wrong? Because that stuff's not water anymore. And that's what I'm saying in this statement over here. Do not change any subscript. Sub is small below, okay? So any subscripts below those small numbers, as that would change the identity of the chemical substance. We couldn't balance the equation by simply putting an extra oxygen on water and forming H2O2. That's not water anymore. That's hydrogen peroxide. Very different stuff. Okay? So, how do I do it then? Well, I'm going to, let's take this little bit and rewrite it. And we've got H2 plus O2 forms H2O. What can I do? Well, I can put big numbers in the front. So notice I've got 2 oxygen atoms. I must put a 2 in the front of that. So I'm now forming 2 water molecules. And that then means, if I tally up, I've got 2 oxygens and 2 oxygens. Hydrogens, well, I've got 2 multiplied by 2, 2 times 2, which is giving me 4 in the product. I must have started with 4 in the reactants, so I must have a big 2 there. So that's, again, 2 times 2, which is 4. And so really, balancing is all only just actually bit of multiplying and counting how many of each substance you've got. Okay? Always focus, remember, please, not ever to go and change subscripts, because if you change subscripts, you are changing the substance you're really dealing with. I'm going to jump across quickly to show you this quick game. You can go and play this, practice. And this is making ammonia. So I'm going to do, I think I need to go back here. There we are. I'm going to have 1 nitrogen. Notice, nitrogen is diatomic. I'm going to have, see, 1 hydrogen. Hydrogen is also diatomic. And what will it form? It's going to form an ammonia, okay, NH3. Looking at it, is it balanced? Well, no, it's definitely not balanced, because can you see I've got 2 nitrogens, 2 blue dots on the left, and only 1 on the right. So what am I going to have to do? And drawing it is very helpful. I must have 2 of them in the products. Now I've got the correct number of blue dots, the nitrogens. Have I got the correct number of hydrogens? No, I haven't. I've got 3, 6 on that side, only 2 on this side. So, is that balanced yet? No. There it is. If I've got 3 hydrogen molecules, that's going to be 6 hydrogen atoms on the left and 6 hydrogen atoms on the right. And it gives me a big smiley face, because yes, I've got this thing balanced. Now, when you work with balancing, feel free to draw them out, okay? But watch out. Diatomic molecules can be a big catch, so watch out for diatomic ones. I've got the link on the notes so you can go and play with those. Let's finish the one we started right at the beginning, which was magnesium plus oxygen forms magnesium oxide. And looking at that, can you identify, I've got the correct number of oxygens on the left, 2, but I need 2 on the right, so a big number in the front, and then a big number in the front of the magnesium as well. So yes, that should be balanced, because I've got 2 and 2 and 2 oxygens, 2 oxygens. It's perfect. Balancing equations should not be a struggle for you. It really shouldn't. It should be something that you say, yes, I can do this very easily. But you've got to start with the correct formula. You've got to start with the correct substances, because otherwise you can count up all you like. You're not going to get the correct equation. So watch out. Write the correct formula for different substances. So we're going to go on to some questions now, and I'm going to focus in this first question on writing the correct formulae. So write formula for each of the following. Magnesium iodide. Magnesium is in group 2 on the periodic table, so it's going to form a 2+ charge. Iodide, here it is in group 17, so it's going to form a 1- charge. And so going across, I would write here Mg 2+, iodide I 1-. Then I write the final formula. Well, I've got to balance the charges, so I need to have 2 of the iodides to balance off with the 2 from the Mg, so MgI2. Next one, copper. Notice they're telling me the charge on the copper. Why? Well, because copper is here as one of the transition elements, and so we don't know what its oxidation state is going to be, but they tell us. Notice it's a metal, so it would always form a positive ion. So Cu 2+, fluoride I can recognize is a halogen, so F 1-, the same as iodide. So the formula is going to be CuF2. I have to have 2 of the negatives to balance out those 2 positives. Next one, calcium sulfate. Calcium is in group 2 on the periodic table. So Ca2+. Sulfate, where is that on the periodic table? It's not. It's a polyatomic ion, so you need to go and learn it. Okay, sulfate, I would remember, is SO4 2-. And so notice that whole thing I can just write down because I can memorize sulfate SO4 2-, and very quickly I'm now balancing the charges. So it's done for me already. CaSO4 sorted. Potassium chloride. Potassium K plus, chloride Cl minus. It's a 1 plus and a 1 minus. They're balanced already, so KCl. Lithium nitrate. Lithium is in group 1 on the periodic table. I'm running out of colors here. There we are. Lithium nitrate. So, lithium 1 plus, nitrate NO3 minus. That's one of those polyatomic ones I suggest you learn. Lithium nitrate, LiNO3. Ammonium carbonate. Ammonium is NH4 1 plus and carbonate CO3 2 minus. Now I've got a little bit of a problem because I want to have 2 of the ammoniums, 1 of the carbonates. But how do I do 2 of those whole things? Because if I put a 2 next to the 4, it's going to look like 42, and I don't want that. If I said 2 multiplied by 4, it would give me 8, but then surely is that saying anything about the nitrogen? No, it's not. So the way you overcome this is put it in brackets. Okay, very easy to do. We write NH4, but I want 2 of them. And then the carbonate, because it's only an individual, it can only need 1. It can be very easily there. Last one, sodium hydroxide. Sodium hydroxide, Na plus, hydroxide, OH minus, and so final answer here, NaOH. I hope that's really helped. You need to practice writing correct formulae. As soon as you've got correct formulae, then you can look at balancing. But you can't look at balancing before you've got the correct formulae, the correct equation. Let's turn to the next question, and I've got some questions here on balancing. So this one is quite easy because they've already given me the correct formulae. Balance the following equations. So ammonium carbonate forms ammonia plus carbon dioxide plus water. That is a decomposition reaction. Notice it's breaking down into simpler substances. And so, all I'm going to really do here is write up a bit of a tally. What have I got? I've got nitrogen, I've got hydrogens, I've got carbons, I've got oxygens. And I want to just count left-hand side, right-hand side. Now, nitrogen, do you notice the 2 over here is multiplying in that whole bracket? So it's 2 times 1, which is giving me 2. But on this side, I've only got 1 of them. So what am I going to need to do is go and put a big number 2 in the front of that nitrogen, and that's going to help. So notice I've said that's 2 times 2, which is going to give me 2. Nitrogen is balanced. Tick it off. We might need to check them because we could come back and make some changes, but nitrogen for the moment is balanced. Let's go to the next one. Hydrogens. I've got 4 times 2. 4 times 2 is going to give me 8. And here I've got 2 times 3 is giving me 6. But to that, notice I've got another 2 down here. I've got a total of 8 all the way there, because 2 times 3 is 6, plus the extra 2 is giving me 8. So yes, hydrogen looks like it's fine for now. Carbon. Let's change colors. Carbon, I've just got 1 there. Notice there's no, just got 1. And carbon, just got 1. That's easy. We're going to change to oxygen. Oxygen, I've got 3 on this side and 2 there plus 1. 2 plus 1 is giving me 3. So yes, the carbon was balanced and the oxygen was balanced. we are all sorted. Notice balancing is really just about counting, but you have to have the correct formula for each substance first. Mindset is, I hope that's really helping you. We're going to take a short break, and then I want to come back and do one more question, and then the challenge question. So go and do that now. Avram.
Thank you so much, Tracy. And a big shout out to Loons, who just came in to check out on on the little Tracy that we have. A big shout out to you, Naughty Loons. Otherwise, Mindsetters, after the break, we'll be announcing our winner from last week's show for winning this awesome Casio calculator. So do stay tuned, because you're about to find out who's the winner. See you after the break. Welcome back, Mindsetters. On the page, we do have the challenge question, so I hope you've gave it your own best shot and see if you are going to answer it correct, because after this, Tracy's going to give us the right answer, but otherwise, you still have the test yourself questions that you need to submit in order for you to win this awesome Casio calculator. But our winner from last week is Progress Mzimba. Congratulations to you. On your way, it is this lovely Casio calculator. So, Mindsetters, you could be next.
Thank you, awesome. And I know mindset is, it's really important to challenge yourself, because otherwise, how are you going to be learning new stuff? So, I've got one more question here, but I think there was a question on the page about that you were asking.
Yes. Here's the question from Banyana. Is nitrite and nitrate different?
Nitrite and nitrate, yes, they are different. So, nitrate was the formula I gave you, and that was NO3 minus. Nitrite, spelled with an I, nitrite, with the I there, is NO2 minus. They are different. I said to you I was giving you the top 7 polyatomic ions, the ones we use most often. But there are a whole list of polyatomic ions. You can go check that out in your textbook, or go on to everythingscience.co.za. I know they've got them there. You can go and learn a lot more, but I definitely want you to know at least those top 7. The nitrate always has the bigger number of oxygens, so that could be helpful. Let's deal with this as we're specifically dealing with the second question here. Lead 2 nitrate solution reacts with potassium iodide solution to form a precipitate, a solid of lead iodide, whilst potassium nitrate remains in solution. And they're asking us to write a balanced equation for this. Don't freak out. Take it one step at a time. Start by writing the individual formulae. And once you've got the formulae, then it's just a matter of counting. So, let's go with writing the formula. Lead 2 nitrate. Well, it would be Pb2+. Nitrate, NO3, 1 minus. Reacts with potassium iodide. Potassium, K+, iodide, I minus. To form a precipitate, a solid of lead iodide. So that's forming Pb2+, iodide is 1 minus, while potassium nitrate remains in solution. So K plus and nitrate NO3 minus. Now all I've done is just write the ions out. They're not yet balanced, it's not yet written as a correct formula, but it's going to help me. So I want to start next by actually writing the formulae. So notice that is a 2 plus, that is a 1 minus. I have to get the charges to balance. So we've got Pb, open bracket, I need 2 nitrates. NO3, close bracket with a 2 at the bottom there. That's saying I've got 2 nitrate ions for every 1 lead ion. Now it's forming, so it's reacting with potassium iodide. Notice the charge is 1 plus 1 minus. That is Ki. Already balanced, already written as a balanced charge. Forms lead 2 iodide. So Pb2 plus, I must have 2 iodides. So Pbi2 2 and reacts, also forms potassium nitrate, KNO3. We now have this yellow, the correct symbol equation, but it's not yet finished because I haven't balanced it. Balancing it is just counting. So I now want to work through PB. How many? 1, 1. Nitrogen. I've got 2 and only 1. So what do? I put a big number 2 in the front there. So 2 times 1 is going to give me 2. Oxygen. I've got 3 times 2 is 6. No more oxygens. There we are. 2 times 3 is also 6. So oxygen is sorted. I've done lead, I've done nitrogen, I've done oxygen. Potassium. We have potassium K. There is 1 and there is 2. So what do I have to do here? A big 2 in the front there, because that's now 2 times 1. And the last one I have to do is iodine, which is 2 on the left, 2 times 1, and 2 on the right, which is meaning they're all balanced. Very, very important mindset is to make sure you have the correct original equation. And notice I wrote the ions out first, and then I balanced each of the charges and wrote the individual substances, and then I wrote the whole full equation with checking the balancing. So once you've got the original formula, don't go and mess with the subscripts. The subscripts are important. You've got to leave them as they are. Now, I want us to tackle this challenge question that I set for you. Again, I gave it to you as a description, and I'm asking you to write the formula. So, aluminium reacts, aluminium, Al, reacts with solid copper 2 oxide. So copper, notice they tell me it's 2, so it's a 2 plus. Oxide is O2 minus. To produce copper metal, so that forms Cu, and aluminium oxide. Aluminium is a 3 plus. How do I know that? Balance a periodic table. And oxide O2 minus. Now it's not done yet. So actually what I'm going to do is I'm going to just take these away so that you don't think that it is actually a correct equation yet. It's not. Giving ourselves some space. Now I want to write the correct original formula. So Al plus. That's going to be quite simple. CuO, because it's a 2 plus and a 2 minus, forms copper, aluminium oxide. Notice here we've got to get balanced charges, overall neutral. So it's going to be Al2O3, because I can get to plus 6 and minus 6. Now it's a matter of counting. So we're going aluminium. I've got 2. So I need a big 2 in front. I have got copper 1, 1. I've got oxygen. Oh, I've got oxygen 3 there. And I need to have a 3 here. So 3 there. Watch out. Is this thing sorted yet? No, it's not, because now I've changed the copper, because the copper is now 3 times 1. So here I have to put a 3 on that one as well. So check it. 2 aluminiums plus 3 copper oxides, forming 3 coppers plus 1 aluminium oxide. And that is the whole challenge question sorted. It's actually not that bad, but you have to write the original equations, the original substances correctly first. So mindset is, I really hope that's helped you. I hope that sorted out representing chemical substances and chemical reactions. From me, Tracy, signing off. God bless and keep well. Abram.
Before you go, I just have one question.
Yes.
And big ups to all the mind teachers that got the challenge question correct. I see a number of them.
Well
so
done.
big ups, guys. A simple question from Tato. Is it a necessity to write the ions before balancing?
No, it's not. You know, it's not a necessity. It's something I do as a practice because it would be very helpful. It just is a balance to check that you're writing them correctly. And I've been doing this for a number of years. So, yes, I would recommend writing the ions, but it's not necessary. Your focus is get the original formula right, and then you can balance.
Okay, for the last time now, Bailey is also asking, based on the first question that we've done, question 1, balancing the equation shouldn't oxygen be 6?
The first question that we've done.
Question 1.
Maybe this one. I'm not sure which one you're referring to. Oxygen, in terms of its charge, shouldn't it be 6? Well, oxygen is a non-metal, so in terms of its charge, it would gain 2 electrons because of where it is on the periodic table. Oxygen over here would gain 2 electrons, so almost like it's making 2 little jumps by taking up 2 electrons to get a filled out energy level. So that's why it would form oxygen O2. Sorry, I say oxygen O2, that's what would form oxygen 2 minus of when it forms oxide, the ion. So maybe that helps, I hope.
Thank you so much, Tracy. And
Blessings.
tomorrow, you know, it's a holiday.
Yes.
So enjoy your holiday tomorrow and
Thank
go
you.
and vote. But for you mindsetters, also tomorrow we do have a live show. So do tune in. It is Life Sciences with Looney. So make sure that you catch that tomorrow. But for today, it's a wrap from us. We love you and peace.